You are going to be guided. So our next speaker is Nathan Ju, who is going to talk about interactive quantum advantage with noisy, shallow Clifford circuits. Nathan, please go ahead and put up your slides.
Okay, this is good?
Yes.
Okay. All right, thank you. So this is joint work with Daniel Grier and Schaeffer. We're both postdocs at the University of Waterloo. And this work was completed while I was visiting the IQC this past summer. Okay, so I want to motivate this talk by beginning with quantum supremacy. And quantum supremacy basically tells us that near-term and noisy quantum computers can solve sampling tasks that are classically intractable if we assume some conjectures. So some examples of these sampling tasks go by the name of boson sampling, IQP, and random circuit sampling. But I want to focus in on this one part about assuming some conjectures. Okay, so many times if you want to prove that the noisy quantum computer is doing something that is classically intractable, we have to start assuming some pretty non-standard conjectures. So I'll just go, for example, in the boson sampling case, we have to assume something called approximate average phase hardness. And many times these types of conjectures are native to the proposals. So these types of conjectures are not as well studied as other complexity-theoretic conjectures like the non-collapse of the polynomial hierarchy. So one thing we might hope to do is to prove some sort of quantum advantage, but without using conjectures, or with using fewer conjectures. So that's what this work is about. It's about comparing noisy and shallow quantum computers against shallow or weak classical computers instead. But this time we'll be using fewer or no conjectures. So I want to emphasize here that we're using shallow or weak quantum computers instead of the typical polynomial time classical computers that are used in quantum supremacy arguments. So there's sort of a trade-off going on here, which is that we're decreasing the power of the classical computer, but we're going to be doing this without using conjectures or with using fewer conjectures. So the first result really in this area is building on this breakthrough result from 2018. And the improvement comes from Bravyi, Gossett, Koenig, and Michel back in 2019. I'll call this BGKT from now on. And basically they show a certain quantum advantage. So basically there's a task that is solved by a noisy constant depth quantum circuit with very high probability. But on the other hand, a classical circuit of constant depth cannot solve this task with probability greater than 9/10. And I'll go into more depth about what I mean here. Okay, so in particular, I'll focus in on a relation task first. So one way you can define this relation task is by, given some input x, you have some constant depth quantum circuit Q. And in this case, it's actually just a constant depth Clifford circuit. And the task is to simply output any y that appears with non-zero probability when you measure in the computational basis at the end of the circuit. So almost by definition, if we have a noiseless quantum circuit of constant depth, we can solve this task. We literally just run the circuit Q and output y. Okay, but things get a little bit tricky when you bring noise into the model. And the noise model we'll be dealing with is a local-stochastic noise model. So this is defined by Aliferis, Gottesman, and Preskel back in 2007. And basically, you can think about one layer of local stochastic noise as just a random Pauli which has, with high probability, low weight. Okay, so we're going to apply some random Pauli operator at every layer of the circuit. And once we do this, we say that we have a noisy circuit. So here, for example, we have a preparation of a 1D graph state on 4 qubits. And we have one layer of local stochastic noise on every layer of the circuit. So this noise model is parameterized by some noise rate P, and we'll be in the regime where this P is a constant. Okay, and the second part of this is the classical lower bound. And it's that we're going to show that, or they showed that a classical circuit cannot solve this task very well. So the types of classical circuit they considered are classical probabilistic circuits. So on input X, they sample uniformly random R, they apply the circuit C and output Y. Okay, and then it's a classical probabilistic circuit with bounded Fanning gates and constant depth. So bounded Fanning gates just means that it has and, or, and not gates, where the ands and ors only have 2 inputs. And constant depth is just the same thing as in the quantum case. Okay, so these types of circuits cannot solve the problem with probability greater than 9/10 over a uniform input. So the randomness is over the choice of the input and also the randomness from the probabilistic circuit. So this is the separation they achieve. But one thing I want to point out here is that bounded Fanning constant depth classical circuits are pretty weak. I mean, in fact, they can't compute logical and, they can't compute logical or parity, or anything that really relies on every single one of the input bits. So we might want to hope for something better, which is that can we increase the separation to compare against more powerful classical circuits? Now, in the setting without noise, the answer is yes. There's a wonderful line of work which shows that a noiseless quantum circuit demonstrates a quantum advantage against more powerful classical circuits unconditionally. However, in the setting with noise, the answer is not so clear. In fact, this BGKT result is really the only one right now. But in this work, we basically promote all these separations in the noiseless case to the noisy case. So we get separations using noisy quantum circuits. So I want to illustrate the situation a little bit better. So again, we have separations between quantum circuits and classical circuits or classical machines. And on the top, we have either noiseless or noisy quantum circuits. And on the left, where they have weaker classical circuits, those are like NC0 or below, and stronger classical circuits, those that are stronger than NC0. So what might some of these classical circuits look like, these stronger classical circuits? Well, we already know what NC0 looks like. These are just constant depth bounded Fanning gate circuits. So they decide they define some complexity class. Strictly containing this class are AC0 circuits. So these are just the same thing, except we have unbounded Fanning gates. So our ands and ors can have as many inputs as they want. Also strictly containing this are AC0P circuits. And these are just AC0 circuits with mod P gates. And these mod P gates have the property that if the number of ones in the input is divisible by P, then it'll output a 0. Otherwise, it'll output a 1. Okay. And strictly containing this are log space machines. And basically, these are just log space Turing machines. And finally, containing this is the complexity class parity-L. And you can think of this class in terms of its complete problem, which is just to determine the parity of the number of paths from a start to an end vertex in a directed acyclic graph. Okay, so now that we have these complexity classes, the situation kind of looks like this. So we have separations between noiseless quantum circuits and weak classical circuits. This line of work also improved this to stronger classical circuits. And on this bottom, I labeled it with an interactive problem. I'll define what this means later on. On the top right, we have the same result that I was talking about before from BGKT, which is a noisy quantum circuit versus a weaker classical circuit. So in this work, it's about filling in that bottom right corner. Can we prove a separation between noisy quantum circuits and stronger classical circuits? And the way we're going to do this is that we're going to promote these separations on the left to noisy separations. And the way we're going to do that is that I'm going to focus in on this paper about interactive problems. We're going to combine some new ideas on top of this BGKT result, and we're going to promote the separation. Okay, so there are really 3 steps to proving a noisy separation. The first is to prove a noiseless average case separation. Okay, so if we have some task I that is solved by a noiseless constant depth quantum circuit, we want to prove that a classical machine cannot solve I with very high probability. So in particular, we want to show that classical probabilistic machine cannot solve it with probability 1 minus delta, where delta is a constant, on a uniformly random input. And again, this is over the randomness of the input and the randomness of the machine. Okay, but it turns out this step will require new ideas, and this is where most of the technical work goes into. The second step of this is to extend the definition of the problem to account for noise. Okay, so with our original problem I, we have some input x, and we want to output something, a lowercase y, that satisfies this relation. We're going to transform this into a new problem that is noise tolerant, which we'll call I prime, which is the extended problem. And the way we're going to do this is, if you recall in the original relation problem, it was defined using a quantum circuit. We're going to encode this quantum circuit into some quantum error correcting code. And we're going to say that some measurements from this quantum error correcting code solve the extended problem if the output, which we call calligraphic y, once decoded, equals the original problem's output, lowercase y. So let me show this pictorially. So this is the circuit encoded in a quantum error correcting code. And once we measure it and we get measurement results, we say those are correct if, once we decode them, they give us back the output for the original problem I. Okay. Now, if we combine these two things, we get a noisy separation, which is that the task I prime is solved by a noisy constant depth quantum circuit with very high probability. On the other hand, a classical machine cannot solve this task with high probability at all. There's this delta, there's a constant delta probability of error. Okay, so let me get more concrete and show our main results. So we follow this exact same framework. So the first thing we do is we prove a noiseless average case separation. We prove that there's an interactive task that is solved by a noiseless constant depth quantum circuit. And if we have some classical solution R, which solves it with probability better than 420 or 421, then it must be solving parity-L-hard problems. So you can think that, if this machine is like an AC0 circuit or an AC0P circuit, or just anything that's weaker than parity-L, it simply cannot solve this problem. Okay, so the setting in which this takes place, you think about it like this. We have an experimenter, and they're interfacing with this circuit, and they want to know whether it's quantum or classical. We know that if it's quantum, it'll succeed with certainty. If we know that if it's classical, it can do no better than 420 over 421. So we have an interactive task. And what that means is that the experimenter gives some inputs in the first round, x1. The circuit will return with output y1. And then the experimenter goes in the second round with an input x2, and then the circuit outputs y2. Okay, so this is just the setup of the interactive problem, for which we show that a classical machine cannot do very well at, or it requires the power of parity-L, basically. Okay, and then we basically do the same thing as before, which is the recipe from BGKT, and we just extend the problem using quantum error correction code. And using these two things in together, we get a noisy separation. We can prove that there's an interactive task that is solved by a noisy constant depth quantum circuit with very high probability. On the other hand, if some machine R does better than 420 over 421, then it must be solving parity-L-hard problems, but under a slightly stronger reduction, where this Q means quasi-polynomial size circuit. Okay, but we can actually extract two results here, and one is unconditional and one is conditional. The unconditional is that we have a separation between noisy constant depth quantum circuits and AC0P circuits. And a conditional one is if we assume this weird complexity conjecture, then we have a noisy constant depth quantum circuit. We have a problem that a noisy constant depth quantum circuit can solve that a log space machine cannot solve. Okay, and this conjecture you can think about as a strengthening of the more well-known parity-L not equal L conjecture. Okay, so this work is really about mainly about this result on the top. This is where most of the technical work goes into. And this is the noiseless average case separation. So the problem setup looks like this. We define it using a 2D graph state, which I'll call a grid state. And we can divide the qubits into two parts. So we call it the round 1 qubits and also round 2 qubits. So the interactive task goes like this. We're going to ask the circuit to measure the first half qubits in the basis x1. So x1 corresponds to some Pali basis measurements, so either x, y, or z for every single one of the qubits. And then it's just going to output something that occurs with non-zero probability, y1. And we basically do the same thing for the second round. We give it bases x2, and then it'll measure and give us outcomes y2. Okay, so almost by definition, a noiseless constant depth quantum circuit can solve this task. It literally just prepares a graph state, constant depth, measures the first round qubits, then measures the second round qubits. Okay. So this task is actually also hard, or very hard, for a classical circuit. It can do no better than 420 over 421. Again, there's one slight caveat here, in that this is actually a promise problem. So it's not that you get any Pali measurements in the first round and any Pali measurements in the second round. It's that there's this well-defined promise set of possible Pali measurements that we give in the protocol. Okay, but I'm going to ignore that for now. And you can think about this result as saying that it is average case parity-L-hard to return valid Pali measurement outcomes of a grid state. Okay, so how do we prove this average case hardness? We're going to do this by doing a worst average case reduction from a parity-L-hard problem. And what I mean by this is that we're going to use the ability to classically solve the interactive problem on random instances, and we're going to use that ability to solve a worst case parity-L-hard problem instance. So in particular, we're going to leverage this machine R that succeeds with probability 420 over 421. And we're going to use that to construct a solution to some worst case parity-L-hard problem, or solve a parity-L-hard problem on every input. I want to make a quick note here in that BGKT also proved an average case hardness result, but they proved that using non-local games instead. So here we're using very different techniques to prove average case hardness. Okay, so let's get into the worst average case reduction. So if we begin with some worst case parity-L-hard problems, the first one is it is parity-L-hard to determine the parity of the number of paths from a start to an end vertex in a layered directed acyclic graph. Okay, so here are two layered DAGs. The top one has even parity and the bottom has odd parity. And something my co-author showed last year is that it is parity-L-hard to determine whether some sequence of C0 gates multiplies to the 3-cycle or the identity. And they proved this using a reduction. So basically, if you have an even parity DAG, the reduction will output some sequences of C0 gates that multiply to identity. If you have an odd parity DAG, it'll output some sequence of C0 gates that multiplies to the 3-cycle. And in turn, we can use the measurement results from the grid state problem to determine whether it multiplies to the identity or the 3-cycle. So we can use measurement results from the 2-round problem to determine which one it is. So that'll solve a parity-L-hard problem. So it goes like this. You have your round 1 and your round 2 qubits as before. And you want to determine whether G1 to Gn multiplies to the identity or 3-cycle. So there's this randomized algorithm gamma, which takes in G1 to Gn and outputs random pallies P1 to Pn. And these random pallies are acting as first-round input to the interactive problem. So we basically give the circuit a P1 to Pm, which we're asking it to measure in these specific Pauli bases. And in the second round, we also ask it to measure in some other bases x2. And you can think about how this solves a parity-L-hard problem in the following way. These random pallies P1 to Pm are somehow encoding whether the original G1 to Gn are identity multiplied to the identity or 3-cycle. Okay, so if you perform measurement-based quantum computation on the left half of the qubits, we know that on the right half of the qubits, we have some state that also encodes some information about whether it's the identity or the 3-cycle. So if you repeat these measurements several times, you can actually learn whether it's the identity or 3-cycle. Okay, but one problem we have is that this only gives us worst-case parity-L-hardness. And the reason is that gamma does not produce random instances to the first-round input. It is a randomized algorithm, but it is not highly randomized. So if you recall, in a worst average case reduction, we want to use the ability to solve problems on many random instances in order to solve a worst case problem. But we don't get that here, and I'll illustrate why. So again, the problem is that gamma doesn't produce random instances to the first round input. So we have this parity-L-hard problem again, which is concerned about the parity of paths in a layered DAG. So if we assume that this line consists of all size n layered DAGs in the universe, and if we pick a particular point on this line, it gives us some layered DAG, we want to find out whether this has an even or an odd parity of paths. That's a parity-L-hard problem. Okay, so we have this other parity-L-hard problem, which is determining whether G1 to Gn multiplies to the 3-cycle or identity. And there's this reduction to the sequences of C0 gates. So if it's odd parity, G1 to Gn will multiply to the 3-cycle. And if it's even parity, G1 to Gn will multiply to the identity. Okay, and then as before, we can give inputs to the first round of the interactive problem. And the way we do that is we sample using this randomized algorithm gamma. And it samples something uniformly from the image of gamma, basically. Now, the one thing I want to point out here is that the image of gamma is pretty small in comparison to the size of, or this universe of all first round inputs to the interactive problem. Okay, so it's not highly random. But nevertheless, we're able to prove something. We're able to prove robustness to small error within the image of gamma. So what I mean by that is that if some small fraction of inputs to the interactive problem will give us bad outputs from the oracle. So let's say this red dot means that the oracle will give us a bad output for this particular input. We can still recover the parity of the number of paths in the original layer DAG. Okay, but this is not enough to prove average case hardness. And the reason that it's not enough is that average case hardness in our setting is a statement about constant error. So we want to show that if the circuit errors with probability 1 over 421, then we can solve every layered DAG problem. But we don't get that. So for example, let's suppose that this red box is where this 1 over 421 lives. So basically, everything living inside this red box means that the oracle gives us garbage output, basically. Well, that means that our output for the first round interactive problem, or our output for the interactive problem on these first round inputs gives us complete garbage. As a result, we can't determine whether the sequence of C0 gates multiplies to the identity or 3-cycle. And as a result, we can't determine the parity of the number of paths in the original layered DAG on top. Okay. So, oops, yeah. So we get the wrong parity on top. Okay, so how do we solve this? Well, we begin with a different problem, a slightly different problem. It's also known that it's parity-L-hard to determine the parity of the number of paths in a general directed acyclic graph. So in a layered DAG, we had some sequences of layers, and you only had edges from one layer to the next. In a general DAG, this rule is not enforced, so you don't need layers. So suppose we want to solve some worst case DAG instance. We want to know the parity of the number of paths. The main technical ingredient we add here is something called randomizing coatings. And this shows up in the theory of cryptography and was discovered in 2006, basically. And we leverage it in the following way. If, for example, we have a DAG with even parity of paths, we're able to sample a uniformly random layered DAG with an even parity of paths. On the other hand, if we have a DAG with an odd parity of paths, we're able to sample a uniformly random layered DAG with an odd parity of paths. Okay, so as you can see, the layered DAGs that we get from this distribution are highly random. And as a result, if we follow this reduction from layered DAGs to sequences of C0 gates, and sequences of C0 gates to first round input to the interactive problem, we also get very random instances. Okay, so this ends up solving the problem of gamma not producing random instances to the first round input, because we've basically randomized this one layer on top, DAGs to layered DAGs. Okay, so we combine these two ingredients, we get our main technical result, which is an average case parity-L hardness. So if ours is a classical solution that is randomized and solves a task with probability better than 420 over 421 over uniform input, then it must be solving parity-L hard problems. Okay, so I'll conclude. So the main technical result is that simulating grid state measurements is average case parity-L hard in some sense. We can reuse some of the noise tolerance ideas from BGKT. I didn't show many of those, but basically we use these ideas to show that a noisy quantum circuit can solve a related task, while the task remains hard for classical circuits or classical machines. And this gives us two things. One is an unconditional separation between noisy constant depth quantum circuits and AC0P circuits. The second is a conditional separation between noisy constant depth quantum circuits and log space machines. Okay, so I have some open problems here. I just have some extra time, so I could go over these. So we show parity-L hardness with a threshold of 420 over 421. Maybe we can go lower than this. And I'm curious to know what is the right number. We have unconditional and noisy separations now against constant depth classical circuits, including NC0, AC0, AC0P. Can we show separations for different problems? So for example, sampling problems. And the final one is, can we base our conditional result on just simply parity-L not equal L? And that's it. So I'll take questions.
Thanks a lot, Nathan, for your nice talk. So there has been a couple of questions. Maybe you can answer this one. For the classical quantum separation, is it possible to go further to larger circuit classes than parity-L problems?
I believe you could prove stronger hardness results, but the one thing you have to change here is that all our circuits are Clifford circuits. And we know that Clifford circuits can be solved in parity-L. So basically, in order to show hardness beyond parity-L, we'd have to use some non-Clifford element inside these circuits. But my guess is probably possible. Yeah.
Okay, and there is this question and some replies. Maybe you can expand on this. In one of the slides, you said C0 multiplying to a 3 cycle. What do you mean by this phrase?
Yeah, sure. I can go to that slide actually. Okay. So suppose you have some sequences of C0s. That we know one thing, which is that swap gates can be, if you have 3 C0s, so like control target, control target, control target, that gives you a swap. If you have a 3 cycle, is like you basically cycle the first 3 qubits using these swap gates, and the identity is just the identity.
Thank you so much. So there is a question for myself actually. So in separating these classical and quantum circuits, for example, in the first paper that you mentioned, they use this non-locality to separate. they show that there are some non-locality properties in quantum circuits that the classical circuits cannot satisfy that non-locality condition, right?
Yeah.
So I was wondering if such a duality can be used in your problem as well.
I'm actually not very sure about that. At least the hardness results are very different. So the way they prove hardness is like directly reducing to a non-local game. It gives you some classical strategy. On the other hand, this reduction here doesn't really use those properties about reducing to some classical strategy. So I'm not very sure, but I don't know. I'm not sure.
Okay, maybe so you have some classical, you are basing your result on some classical properties of these classical circuits to prove that, right?
Yeah.
Okay, there's not anything like showing something is easy for these quantum circuits, and for example, you are not using non-locality properties or anything like that.
Directly in our reductions, we don't really use non-locality, as far as I'm aware.
And so I was also wondering, so whether you know that the other papers, like the second paper that you mentioned, what are their main techniques?
Which paper are you talking about?
So in your first slide, you had, I think in the first or second, you had some examples in a table to separate the classes. So I was wondering what kind of techniques they use to separate the circuit classes. I mean, to show the hardness for classical circuits.
Yeah. So basically, so I'll list them. So basically, I know for a fact that like BGKT, BKST, and maybe BGK, they all reduce to non-local game. So it gives you a strategy for a non-local game. The one that is different, as far as I'm aware, is this GS21. And that's the one where I try to explain in this talk. And that one doesn't directly reduce to these non-local games again. But pretty much everything on the top reduces to some sort of non-locality argument.
So for the circuits, for the classes that they don't use this non-locality, what is the intuition behind proving this hardness problem? So the one that is in red, GS20.
Yes.
So what is the intuition behind showing the hardness for classical circuits?
I think this slide was a good example of that. But basically, we prove some sort of like computational hardness, which is that we can solve a computational task which is complete for parity-L. We do that is we basically perform measurement-based quantum computation. And our measurement-based quantum computation, if we have a classical device that's simulating this, it can be basically leveraged to solve this computational problem. So this computational problem of basically determining the parity of number paths in a layered DAG. So this is where I don't know if there are any non-locality arguments going into this, because it's simply just some like computational reduction in a sense. There's no like violation of some like non-local game or anything like that.
I see.
Yeah.
Okay, thank you so much for the answers. So we don't have any further questions in the Slack channel. So I was wondering about the problem that that the quantum circuit solves. Maybe you can expand on that. Is that problem of like practical use or?
So practical use, I mean, I don't really think so, because this problem can be solved like in polynomial time classically, basically. So like you can use your laptop to solve this problem. And in terms of like applications, I mean, it's just measuring some 2D grid state. I don't immediately see any applications for this.
Okay. Thank you so much, Nathan, for your nice talk.
Of course.